Okay, so welcome everyone to Boston Clojure Group. It's been a while, so we're really encouraged to see so many people who signed up for this event. It promises to be a good one. So our meetup this time is about Clojure and Temporal, and our speaker, Greg Haskins, created a Temporal SDK for Clojure. He's co-founder and CTO of Manetu. I hope I said that right. Where they use Temporal. So without further, I'm going to pass the baton to Greg Haskins.
All right, thank you, Mark. Thank you. Hi, everyone. Name's Greg, as Mark said, and I put this presentation together, and I hope you enjoy it. So I guess we already covered that. So tonight's agenda, I've split up into three parts. First is an introduction to Temporal itself in general terms. Then we're going to dive into the Clojure SDK for Temporal and finish up with a demonstration of code that I've actually put up on my GitHub page, so you can pull it down and look at it yourself if you'd like. So let's begin. So part one, introduction to Temporal. If you're already familiar, I apologize. So just some high-level concepts and whatnot so that the SDK conversation makes more sense. But first, a description of what Temporal is. With the recognition of when you're building distributed systems, that there's various things like hardware failure and networks being severed and power going out, etc. Certain domains for application development would like their applications to be hardened and fault tolerant against this, and Temporal helps you do that. So how does it do that? At a high level, the way I think of it, at least, is it's a framework for providing durable checkpoints and replay to your code. It does so in a manner that's largely transparent, or in many ways transparent to your code. So my background is I've worked in the telecom industry, I've worked in financial services. So telecom industry in particular, they're always building fault tolerant systems and whatnot. I wish I had this tool 20 years ago when I first started out. It does a lot of things that are needed for building really resilient applications in a very elegant way. It's a very, very impressive project. And we're going to get into how it works today and how you can use it with Clojure. One of the defining attributes of Temporal, I would say, is that you code your workflows and things like that we'll get into in natural programming languages, right? So they have SDKs for, I don't know what the number is, probably at least a dozen different programming languages. There wasn't one for Clojure, so that's what I worked on, and that's what we're going to talk about tonight. But there are programming SDKs for a variety of languages out there, so you're coding in kind of your natural language of your business logic, as opposed to a domain-specific language like BPMN. Temporal itself is designed with kind of the modern web scale best practices for horizontal scalability and reliability, et cetera. So it's not going to impose a liability to your code. It's going to work right alongside it, helping you build really reliable applications. So this slide is really just to introduce you to some of the concepts. We're actually going to go into a little bit more depth in some of these in the following slides. But at a high level, some of the entities that you'll see when you are working with Temporal are things like workflows and activities and event logs and task queues. So just as a high level, kind of to wrap your head around what we're talking about here, workflows and activities are kind of one of the core concepts to understand. Think of them as functions that you're defining in your whatever logic, whatever language you're using. In this case, we'll be talking about Clojure. So they're functions, and they run inside your own infrastructure, right? So there's a concept called the temporal worker, and that hosts your workflow and activity functions, and it connects the worker processes connect to Temporal through a concept called a task queue, right? So the task queue is kind of like a Kafka topic or message topic. you're subscribing to. And so the temporal server itself can host different namespaces, with each namespace having different task queues, et cetera. So you kind of split out your work that way. But generally speaking, you're defining workflow functions and activities. You're putting them in, running them inside a worker process on your infrastructure, and then connecting that worker process to Temporal to guide its operation. So the other part of the equation is the client. So clients can invoke workflows to have them perform services. There's the notion of querying and signaling and canceling as well. So clients can interact with the workflows that you've defined. It's kind of like an RPC type style mechanism, except rather than invoke the code directly as a local process or remotely as a standard RPC, you're going through the temporal service. The back end of Temporal is where kind of the magic happens. It will orchestrate the execution of your workflows and activities as appropriate. But one of the most important things it does is it's maintaining an event log for your workflows as they execute, and that's what gives its that durability and that replay capability that's important for maintaining these resilient processes. The last part here, as I just mentioned, is you're usually going to use it in conjunction with some other kind of like data center orchestration layer, like Kubernetes. So your processes and the temporal processes, and even the backend persistence layer, like Cassandra, are spread out across availability zones and kept running, et cetera. So it works very nicely with things like Kubernetes. Now, this is a really simple sequence diagram for a hypothetical operation. We have a client that wants to invoke a function, a function to do something. And let's just say that this function is you're going to create an object in a database and send out a Kafka event or something like that, right? So if you're going to do this in straight Clojure, maybe you have a REST endpoint or a gRPC endpoint or a Kafka client, et cetera. It receives a message and it decides it's time to do this. So if you just did it in plain Clojure code, you might call the database function to update the database table, call the Kafka function to send the message, and be done with it. And this is the temporal version of that. So we're just we're invoking that operation, which in this case I called workflow A. We're invoking that through Temporal, right? So the client using a temporal client as part of the SDK basically says, I want to invoke this workflow, and then Temporal will orchestrate the actual communication to your worker to start that workflow. But basically, in this case, it's just progressing through it. We have a very simple, two activities that we'll talk about what that means in a moment. But, say activity B represents that write to my database, and activity C represents the write to Kafka. This is just going to progress through and, in sequence call the database update and the Kafka update and exit. And that's all well and good. And actually, one thing I should point out is the event log here on the right is what Temporal is kind of maintaining in the background as these different interactions occur. So we can see, we kind of start with the sequence 1 here, where the execution of the workflow A is started. And then we kind of progress through different key points where the activity for activity B was invoked, et cetera. And so Temporal is maintaining this log for us as these different interactions occur. Now, if we didn't have to worry about failures and whatnot, this would probably be more complicated than if I had just called the database in Kafka directly. But of course, the real world is not so nice oftentimes, and we can have different types of failures. So what I've done here is I've taken the same basic flow, except I've introduced a failure somewhere in the middle here, in this case, right after we had finished calling our activity B, which kind of represents my database update. So, maybe the power supply went out on the server, or the motherboard died or whatever, or maybe you had a memory leak and your code crashed at that moment. It doesn't matter what the reason is. Sometimes things fail, right? And so in this case, the worker process A had initially received the request to start processing this workflow, and it died. So when that happens, Temporal will start to go through a remediation process and schedule that to run somewhere else. Now, this can happen. This can be a situation where you had multiple workers all listening on the same task queue already. So maybe I'm running 3 three workers across three availability zones, and they're all listening. So as soon as one fails, we're going to very quickly find an alternate worker process to take the task. Or it could be, you didn't have a backup running, but Kubernetes sees the pod dies and restarts it. You can have different properties for, failover latency and things like that. But regardless, when a worker becomes available on the task queue, Temporal will restart the process or replay the process and can have you give the ability to continue on. So one of the things I'll point out here is that if you look in the original picture, we had this kind of real basic synchronous RPC-like flow. Client comes in, invokes the workflow invokes activity B, waits for the result, then it invokes activity C, waits for the result, etc. And we see that happening up here at the top of the picture as well. So workflow starts, it invokes activity B completes, we start to receive the result, and then something happens, it goes down. So when that happens, Temporal actually replay the log. So from worker B's perspective, the process doesn't know the difference, or it doesn't need to know the difference between the initial invocation or a replay. It's going to receive the same sequence of events that it had already started to receive. So in this case, the initial invoke comes in. So the initial parameters that were submitted by the client are maintained in the log, and they're resubmitted. Workflow A would then once again ask to invoke activity B. But in this case, you can see we jump right from sequence 3 to 5. There's no reason to rerun the database update or activity B's update because it already completed and was made durable, right? So the result of activity B was previously recorded durably in the log at step 4. So Temporal just replays the result. So from worker B's perspective, it asked to invoke B and it got back a result. And it will go through this for any of those things that have already completed durably. And it helps the process to basically rebuild the state to where it was before it crashed, and it will continue from where it left off. So in this example here, down here it's step 6. We're now into we're into novelty again. We're doing new operations that weren't done before. So we continue on, invoke activity C, that gets a result, and then the workflow completes and the client gets the result. So from the perspective of the client, other than, if you were measuring latency, there's no difference. They invoked workflow A and they got a result. Temporal helped, mask that particular fault of worker process A dying in the middle. And we're going to go through what that looks like to build applications that can do this. So, high level, again, a little bit more details. Workflows are really, your high level, they're your resilient program. So these are the things that those functions you're defining that are designed to be able to tolerate faults and be able to handle the replay and the invoking of activities, etc. As I mentioned, workflows can do things like invoke activities like we just looked at. They can receive signals. Signals is basically being able to send a message with a payload into the workflow. They can be queried, they can be canceled, etc. So the workflow logic is dealing with these different concepts like invoking activities and receiving signals. And they also can do things like wait for certain events like time passing and things like that. Workflows are designed to be really lightweight. You can have lots of them running on a given system, even within a single process. And they're designed to be long running. They can be long running, like you could have them really weeks, months, years, whatever. And they're designed to be resilient to system crashes or restarts, etc. And they can also be, they don't have to be long running. They could be just doing multiple operations in which it's important to do all of them. Like my example of updating a database and sending a Kafka message and not forgetting to do one or the other. So again, Temporal will invoke those workflow programs at the right point, and your application doesn't really need to know the difference between that initial invoke or the replay invoke. It just handles those events. I guess I already covered that. So you really don't need to be concerned with replay when you code these things. Again, the information is actually available to you. You can introspect the state and find out that you're going to retry versus a an initial invocation, but generally speaking, you don't have to care. You just write your logic in a straightforward manner, and whether it's a replay or not doesn't matter. But one thing that is key is that when you're writing workflows is you need to understand that there is a few constraints. So one of the constraints is determinism. This actually, Temporal and Clojure are a great match because workflows kind of have a functional like paradigm. They need to be based on just the inputs and the outputs as opposed to doing things with side effects. It's not a perfect analogy, but it's a pretty good analogy where they're kind of like pure functions. So what we'll show in a few moments is that part of what makes this magic work is that as you're interacting with the system, inputs and outputs to functions are automatically recorded in the event log. And what the determinism constraint really means that, for a given input, the workflow needs to behave in the same way, right? So in other words, in my example before, we had, workflow A that invoked activity B in C series with activity C and then exited. So you would want to make sure that, for a given input, at least with that version of the code, it's always going to invoke B and then C. It's never going to do C and then B or C and leave, or it has to do the same deterministic operation. So you're building it in a manner that it has to be expressed in terms of its inputs and behave the same way. And the other constraint is related to what I like to think of as kind of the core async lightweight process kind of problem. So, if you've ever used core async or any lightweight process system, they usually have several different properties. So one property is there's usually a high instance to CPU ratio. You can run, thousands of, Go routines on a single core if they're IO centric. Obviously if they're compute centric, that won't be the case. But, if you have a IO centric lightweight processes, you can run a high ratio of instance to CPUs. That's on the positive side, but you also need to be careful about your IO constructs because most of those lightweight processes are predicated on controlling the IO in some way that they can efficiently park or sleep, right? So core async, you can wait on a channel very efficiently. Same thing here, like you can have many workflows per core. But you need to sleep those workflows on the constructs that are provided by the Temporal SDK, right? So determinism and kind of the constraints around sleeping are the two gotchas. That's a little bit, different, not different, but you just need to be careful when you're building your code that you don't violate one of those rules. So, and related to that, you also, don't want to use, kind of the native threading primitives. So the workflow context itself is a very carefully managed thread by the Temporal framework, and it's actually a good thing in general. Like if you follow the rules with respect to the workflow context, certain problem domains like the order that you receive signals and queries and things like that become very simple. If you were doing asynchronous programming, it would be a lot harder. So once you actually start following the rules for not doing async threading primitives within the workflow, the logic of your design actually becomes simpler, which is what I found. So, there are ways to block and synchronize on the thread. You just have to use the ones provided by the framework, right? That's what it comes down to. So determinism and kind of blocking IO primitives are the two things that make workflow a little bit different from just pure, normal Clojure code. One other concept I wanted to highlight here before we get into the details, because it will be key in a little bit when we talk about some of the constructs we want to use, is the notion of a workflow ID. So every workflow has an ID. It actually has, there's the workflow definition, which is your definition of your function. There's a workflow ID, which is an instance of that function running. And there's actually what's called a run ID, which is separate from a workflow ID. But the workflow ID is really a critical function because the Temporal platform actually guarantees that there'll only be one instance with that ID across the cluster. And because of that, we can actually do some really powerful cluster coordination things with it. And it's also important for other reasons too, like if you want to be able to send a signal from one workflow to another, you need to know its ID, et cetera. But the cluster coordination is really the key thing that I wanted to get across here. So every workflow has an ID. Platform guarantees there's only one in it at a time with that ID. So activities are similar to workflows in a few ways. You're defining these functions and registering them with the temporal platform, and they can be invoked by the temporal platform in a similar way. What's different is that activities are invoked by workflows, as opposed to workflows can be invoked by other workflows or by clients. So activities are subordinate to a workflow. They're where you do kind of your non-deterministic normal closure type of thing. So when you need to do that IO to the database or to send a message to Kafka, et cetera, you're going to put those in an activity. They're generally speaking kind of just your normal closure code. This is where you're going to do your IO, things of that nature. So when you're in activities context, it's much more, you don't have to think, it's just standard closure at that point, which makes it easier. So you're kind of designing at the top level a workflow that's expressed in terms of, the activities, and the activities are kind of the workhorses where the work, where things are changing state and sending messages and things like that. Signals are another key concept. We talked a little bit about those. That's a way to send a payload from either workflow to workflow or from client to workflow. You can send a message in just like you can send in arguments when you call a workflow. When you do, they become actually part of the event log. So, if I'm sending, my example where I just had the client invoking a workflow and then it fired off 2 activities and exited, let's just say I had in between sending activity B, it paused and waited for a message and then sent activity C. If something sends a message, that message actually becomes part of the event log, right? So during replay, even though the client might have come and gone, maybe a Kafka message was received, that Kafka code looked up the workflow ID, sent it a message, et cetera. Like that signal becomes part of the event history. So if that workflow were to be replayed, the new instance of the worker that's running it would actually see the signal received again, right? It becomes part of the history of that flow. And there's a lot of really powerful things we can do with this. I'll talk a little bit more in depth about this when we get to the closure part. One of the things I did want to mention, that's the last point here, which is there's this signal with start concept, and that works in conjunction with the workflow IDs. And that's really powerful for coordinating, resources in the cluster. So I'm going to talk about that when we get to the closure part. So Clojure SDK. This is available up on GitHub under my company's GitHub page, Manetu, Temporal Clojure SDK. There's reasonably decent documentation there, so hopefully you'll find that that's true. But certainly any questions, just reach out to me. But the history of that SDK, first of all, it's unofficial, right? So it's not endorsed by the temporal upstream guys at all, but I have shared it with them, and they do link to it from the community page, et cetera. But it's unofficial, so it's the unofficial Clojure SDK, or it's a unofficial Clojure SDK. There might be others. It was developed by my company and released last year. We use it in production, so it's it's battle tested. It's still new, but it's battle tested. It's built on top of the Java SDK. No big surprise, right? All of us doing Clojure will leverage Java code whenever possible to get extra velocity. So we did the same here. It's a pretty small community, but it's growing. I get a couple new stars every week or so. Still pretty small, but it's growing. One important thing to understand, though, is it's designed for closure to closure use. So I tried to build an idiomatic Clojure SDK, making it as easy for Clojurists to use, but it really does assume that you have closure on basically all sides of the equation. So the clients, workflows, activities, et cetera, are intended to be closure. And that's because I did things like I used nippy encoding for sending data across and things like that. So some of the SDKs are designed for heterogeneity, so you can have just string-based references or JSON encoding, and they'll work Golang to Python or whatever. This is not that. So if you need that, this is not the SDK for you. For us at Manetu, we're building microservices that have like a CQRS pattern. So we'll have, one Clojure code base per microservice and multiple personalities, and those things are talking to each other by having like gateway code send, commands to a command processor, et cetera, but it's all Clojure to Clojure. So that's what worked for us. If you need heterogeneity, this won't work for you. I'm going to apologize for that. But what does this look like? So super simple, and this is a very silly example, but super simple composition of a workflow. The SDK provides a few different macros. One of them is def workflow, right? So def workflow is an important one, obviously. So you're going to define workflows using this macro. It has defn like semantics. You're defining the name of the symbol and then some input arguments in the body, similar to defn. But a few things that are happening here is that under the covers, when you declare a def workflow, I'm auto magically registering that with Temporal for you, right? So in some of the SDKs where you don't have the magic of Lisp, you see this generally in two pieces, right? One registering the function and then another part that explicitly registers the function. I do that for you magically in the SDK by default. You can actually turn that off if you wanted to do it yourself, but the default mode is, you declare def workflow and I'll automatically register that as an invocable workflow with Temporal. But otherwise, it acts like a defn, other than, what's in the body of that defn has to adhere to those constraints we talked about for determinism and synchronization primitives. But otherwise, it's pretty straightforward. So a couple of key points to highlight. I mentioned it before, but calling it out here, one of the things that's magical about Temporal is that, inputs and outputs automatically become part of your event history. So if someone were to invoke this particular workflow, you can see here, I have it's a silly example for a money transfer example. And it has 3 inputs passed in for source account, destination account, and amount. So if someone were to invoke this workflow and they specified the source account, destination account, and amount, those become part of the event history automatically, right? I don't have to do anything. The client just calls it with the parameters of natural idiomatic closure with a map. The map automatically gets serialized and made part of the event log and passed through a function like this. Likewise, what the function evaluates to is the return value. So on your inputs and outputs, it's basically anything that NIPI can encode, which is, I haven't encountered anything that it can't encode. But I mean, keywords, strings, maps, whatever, in or out, you can do. One thing I should mention here, though, is that, when you're building these things, you are building a contract, right? Because your clients and your workflows are decoupled from one another at one level. And they're also decoupled from themselves over time, right? So it is a contract, just like if you're building an API, you need to settle on a schema and then kind of stick with it. You don't want to just ad hoc change things because it is, a contract. So if I change the name from SRC to, spelling it out, that breaks the contract. I want to be careful about that. There are ways to manage contract evolution or schema evolution. But just to be aware of, you are expressing a contract, so change it with care. Now, this is a actual full complete program of essentially hello world. In this case, hi Bob. But what I want to point out is kind of the key details. So ignore the right-hand side for a moment. I'll talk about that. But on the left-hand side, this code is, like I said, a complete program. So if we look at the components here, there's a few things. So on line 11, you can see I have a def workflow definition, and I've defined that. Line 7 is similar to def workflow as a def activity. Same basic idea, we'll automatically register that with Temporal, et cetera. So now I've set up an environment that has a greeter workflow function for workflow and greet activity for an activity function. And because of the macro, they're automatically registered. So now it's a matter of providing a worker instance to serve those and providing a client to invoke them. So looking down at line 17, we just have an example of doing that. So line 18, I'm calling create client, which comes from comes from the Temporal Client Core namespace. You can see up here. So I'm creating a client instance. And now this is, this is a bit contrived because I'm the worker and the client. Normally you might not have them together, but in this case I do. But I have one client instance that I've created on line 18. And then on line 19, I'm calling worker start, which comes from the temporal client worker namespace. It takes a reference to that client that we created. Once I do that, once I call worker start, assuming it all works, that is now a live worker, communicating with temporal on the back end. I should mention by default, it assumes temporal is on localhost. That's why there's no explicit pointer to where my temporal server is. Obviously in real world, you're probably going to say it's, it's some DNS name somewhere else, but for localhost testing, this works out of the can as is. So I'm attaching this worker to a specific task queue, which I've named, my task queue. And that means, I could have, as we talked about, multiple workers attached to that same task queue, and they'll be, able to service these requests as a cluster. In this case, it's obviously just one instance I'm creating, and it will listen on that task queue called my task queue. Line 20, I'm calling basically the first kind of task of a client to actually create a workflow. So line 20 is now switching modes to be the client side that wants to invoke that workflow. Again, that wouldn't necessarily be back to back with the worker in the real world, but it is in this example. But you can see the create workflow takes, again, the client instance that we created on line 18, and it specifies the greeter workflow symbol that we declared in def workflow. So that's actually one of the other things that makes this kind of Clojure specific, is that under the covers, Temporal's registering the string name of a worker function, and the clients are invoking the workflow by string name. But I'm doing the symbol translation for you as part of the SDK, right? So the def workflow takes a symbol to intern, and I turn that into a string when I'm registering it, and likewise the client turns it into a string when it requests it, et cetera. So that's part of the magic behind the SDK. But essentially, that's what's happening there. Is I'm saying, I want to invoke that specific workflow, and in this case, you can see I'm also specifying the task queue that workflow lives on. So generally speaking, both sides are aware of the context. They're going to connect to a specific temporal server on a specific temporal namespace and talk to a specific temporal task queue to kind of connect the pieces. So my worker is now running, listening on that task queue. This client calls create workflow to invoke it. However, invoking a workflow is a two-step process. So you can see here, line 21 calls client start on the workflow. The reason why it's in two pieces is because there's different ways to invoke a workflow. This is the vanilla way. I'm creating the workflow instance and then starting it. But there's also that signal with start method that we spoke about, and there might even be some other reason too. I think those are the two primary ones. But anyways, because it might vary in how you start, it's a two-part process. So create the workflow instance, and then we call start to invoke it. Now you can see here the input. The last parameter in is a map, in this case named Bob. Again, this is going to be specific to your design. I'm just doing NIPI encoding, so you can pass any NIPI encodable value here, strings, maps, keywords, whatever. I generally use maps. I'm sure most of you would as well. I'm passing in this case, a map that just says my name is Bob. So at the moment that I do that, that's going to actually go out to Temporal and kick off the process of running that workflow. Temporal is going to come back, find a worker on the task queue that's listening, which we know is ourselves from the previous work we did, and it's going to invoke that function. So the end result of calling line 21 at some small interval in the future would be that this function starts running up here on line 11. So a few things about that. Like I said, everything, basically everything is NIPI encoding, so I can pass in whatever arguments I want. They become part of the event history. I can return any value I want. They become part of the event history. So in this particularly silly example, I have a map in which appears on line 12. You can see I destructured the input to get the args. So this args key actually would contain the entirety of the args that I passed in here. So I expect this to actually be a map containing name Bob. In this silly example, I don't actually care about the args because I'm just going to pass them verbatim onto the activity when I invoke it. So I invoke the activity called greet activity, just passing through the args. So you can see up here now on line 8, when temporal invokes this function, I can now destructure, or I choose to destructure the arguments to get that name value out, and I just return a string. So, in this case, it's maps in and strings out. It can be whatever you want from a NIPI perspective, and that will all work. Now, a few other things I'll point out. Because the greet activity evaluates to a string, high name, that's what it's going to return. And because greeter workflow evaluates to essentially whatever the invoke returns, which we know from this is going to be a string, this is returning a string. So the result of this workflow would be a string as well. And you can actually get that result with this getResult call, right? So I'm calling that here with the workflow instance, and that will block until that workflow completes. So for synchronous RPC type flows, you're going to be using typically that getResult to block the client until the workflow completes. Everything is actually on the next slide. I cover this a little bit more, but everything's promise centric. Many of the SDK calls return a promise. That's why you see the derefs happening here. Now, you may recall from my earlier warnings about blocking and whatnot, the derefs are safe. There's a few rules about them, but the way I built the SDK is I overridden the iDref protocol. So this actually ends up being safe to block on in the workflow because it's built using the Temporal SDK primitives. So in this example, end to end, we're invoking the workflow with the input parameters Bob. We're calling the workflow runs and then blocks on invoking the activity. So this will block the workflow until the activity completes, and this will block the client until the workflow completes, and we end up with the value. Now, super high level on the right-hand side, what you're seeing is the temporal UI. So there's a UI element that's part of the microservices that come with temporal, and you generally don't need it for any it's not part of the production flow, but it is a helpful debugging tool, right? So if you have this UI component running, you can introspect the workflows that are pending or have completed. You can look at their status, et cetera. So that's exactly what I've done here. I've actually run this program and then looked at the actual workflow. And you can see here, some details like, here's the event log, right? We can see the workflow execution started, referencing the greeter workflow name, et cetera, and you can follow it through. So if you're ever trying to debug what's going on in your workflow, it's a very helpful thing to pull that up. But anyway, that's in a nutshell, the major components of writing, a reliable program in Clojure on top of temporal. Obviously, beyond Hello World, it's a little more complicated, but same basic principles are at play. As I mentioned, most of the SDK calls return a promise. So I did that so that you could facilitate, promise chaining and parallelization, et cetera. So they're all based on that. So we can do things like, aggregate functions like all or race for running things in parallel. I integrated with the Funcool Promesa library. If you've ever used it, it's hopefully relatively idiomatic Promesa kind of constructs. There's a few things I had to add to work around some of the limitations of blocking and whatnot that we spoke about. So you'll see there's a temporal.promises namespace that has some of those utility functions and helpers. Like actually to that point, you can see here this TP all, which I didn't show my requires above, but TP is the temporal promise namespace and P is the Promesa namespace. So like you can't use the Promesa all in race, you have to use the one I provided in the SDK. But overall, it is very much like a Promesa flow if you've ever used Promesa. So in this example here, I'm just showing launching 3 activities A, B, and C in parallel and then blocking until they all finish. Your mileage will vary depending what you're trying to do, but by having it as a promise construct, you're very flexible in deciding to do things as scatter gather or synchronous or whatever you want. There is a link here to the documentation where I talk about some of those limitations. And I will be sending these slides out after, so you'll have all these links. Signals, we talked a little bit about those. So signals are that mechanism for sending a payload into your workflow. When you want to use a signal, there's a few things to be aware of. So the first is that any given system, any given workflow rather, has what I call a signal context, and that's passed in the input parameters. So if we recall from the earlier, one of the earlier examples is, you can destructure the args that were passed into the workflow, but you can also destructure the signal context. So that's what I'm doing here. This signal context is optional. You only need it if you're actually going to interface with signals. If you don't, you just ignore it. But when you're going to use it, you extract it out of the context of the arguments. And then there's a set of, less than bang, greater than bang, core async kind of inspired functions that I've written in the temporals and signals namespace that you can use to, wait for a signal or send a signal, etc. I guess it's debatable whether it was wise to overload, to use the same name as core async, because it made sense when I wrote the SDK, but then when you're looking at code later, you're like, it's easy to confuse that. Is that a core async channel receive or temporal one? But anyway, that's how I did it. So that's how it works today. But again, these, since they're designed, any of the primitives that we've provided with the SDK are safe to block on. So, dereferencing a invoke or waiting on a signal or calling the await function, anything that's like part of the SDK is safe to block on this. So this is one of them. I can put my workflow to sleep, and I can do things like optionally specify a timeout, etc. So you can use that construct to great effect in designing, your workflows. Like we at Manetu, we have this notion of a vault, and a vault can have an optional expiration date. So I use a workflow with a loop, essentially waiting on a signal, and the 3 outputs, the 3 outcomes of that waiting on the signal are either times out, which means it's time to expire the vault, or it gets a message, and the message can either be cancel the expiration or update the expiration date, right? So you can build all kinds of like interesting primitives on that that basic concept, but that is a safe way to kind of do time-based management and interface with the outside world. Context is another kind of helpful little thing that's in the SDK. All context is a way for you to attach something meaningful to your program, and it will be passed back to you when an activity and or workflow are invoked. So, because temporal is invoking the workflows and activities as appropriate. So if you're, starting up your worker and maybe you need to initialize a database connection or something like that you expect an activity to use in the future, the context is a way you can pass it, that open database connection or whatever you need. So we use that extensively at Manetu for those kinds of things. It's not interpreted by the platform in any way. So like you can see here, I've just given it a map of foo and bar, and that just appears over on this side. So it's just there for your use. You can ignore it if you don't care, but most of the time I think you kind of need it. One thing I should say is I made the API for the def activity and def workflow macros consistent in that they both take a context as the first parameter and then the params as the second. I don't know how wise it was on the def workflow side, because using a context variable like that on the workflow invites non-determinism. So in fact, I never end up using it, for that reason, because it's a bad idea. Like if you want to pass something to a workflow, you should pass it in the arguments so it becomes part of the event history. I might remove it from def workflow in a future release just because it might have been unwise, but that historically it's there because I was trying to be consistent. No good deed goes unpunished in this. So side effects are another feature of Temporal and exposed through the Clojure SDK. So a side effect is, it's the best way to describe it. So, we talked about workflows invoke activities. Activities are really where you want to do, kind of the bulk of your heavy lifting. The workflow is really kind of just to orchestrate the activities. A side effect is kind of like a lightweight activity. So when you call side effect, it has properties like activities in the sense that, the ins and outs, or at least the outs, become part of the event history. It's unlike an activity in that it's meant to kind of run something very short and very, very like kind of local to the code. So use it for things like, generating an encryption key or a UUID or a timestamp, things like that are non-deterministic, but not heavy enough to need a full activity, to launch off an activity to do it. So there's a side effect API. You can see here on line 8, it's just, there's the primary thing is to use invoke, and it takes a function. In this case, I'm using the Java time API library to create a timestamp. That's actually a dumb example because I already provide a now function in the side effect namespace. So there's a built-in function for generating UIDs and timestamps already in the library. So if you need a timestamp or a UID, you can just use those, but it's super simple to invoke any side effect you want. So just for clarity, I just called it out here, but so again, it's basically a way to get non-deterministic values computed and added to the event log. But it's very cheap. So like the reason, one of the other things that's different is like it's not meant for long running things, because we didn't get into like timeouts and things like that, but it's charged against the workflow's time. It's not, as opposed to being a separate thing like an activity. So it's really meant for like quick things, like generate an encryption key and done. But anyway, it's super helpful. I use them all the time. So because we're generating UIDs and things like that all the time. So one of the things we should talk about next is idempotency. So, in my earlier example, we had, that simple workflow. It fires off activity B, and then it pauses, waiting for that, and it fires off activity C, pause, wait for it. When you're building these activities, you want to be aware of the fact that the temporal platform is really giving you kind of at least once execution. Right? So if you use Kafka and familiar with the terminology, they tell about like, or really any messaging system is, at most once, at least once, or exactly once. I would classify Temporal's behavior as at least once execution. You're generally speaking, because of the robustness of the system, barring that the sun doesn't go supernova or something like that, it's going to eventually execute your activity. It will execute it at least once, but it may execute it more than once. And the reason why that would be true, I guess, should be, probably obvious if you think about it, just because the nature of it. You're invoking an activity, the invocation becomes part of the event history, then your function has to run and does whatever it does, and on its way out, after it gets to a certain point, the exit event becomes durable as well. So there's a window of time where your activity, may have started and partially run, or even completely run, but not come all the way out to be durable on the exit, and there's a failure which will rerun the activity. So you want to design them to be aware of this fact that it's at least once, and either make them idempotent or in other ways tolerant of at least once behavior, right? So, a couple tips on that. This upper left hand side would be an example of what not to do. In this case, again, my really stupid financial examples are naive, I know that. But this def workflow for a withdraw operation has a single invoke of a debit activity, and inside the debit activity, I'm basically read, modify, and write the database. You wouldn't want to do this. You probably can see it already, because if this were to be run multiple times, let's say we failed right after the database write occurred, but we hadn't exited out of the function, you could end up with a double spend, right? So the temporal platform then runs the function again. It reads the value that was already mutated and then subtracts it again, right? So you get this double spend problem. You can very easily work around this by slightly restructuring the code to what I did in the lower right-hand side. in this case, I'm using two activities, one for the read function, one for the write function. And my workflow is now, now you can see me using the promise chaining here. I'm invoking the account read, and the result of that read then becomes part of the durable event history, right? So let's say my balance is, I'm doing a withdrawal of $100 and my current balance is 1,000. So when I do the read, the $1,000 balance becomes part of the event history. And so when I get to this write function, I'm computing, 1,000 minus 100 equals $900 as part of this is now deterministic because the 1,000 is in the event history. So if this were to replay, I'm going to get 1,000 every time, and then I'm computing 900 every time. So the inputs to account write are now deterministic and idempotent. Real world, you need to do more things to protect here, but you get the idea. So, because I put the database read in an activity like that, it became part of the event history and made it deterministic and made the right idempotent. So, obviously your domains are going to be different, but you want to think about things this way. It's like just a small shift, and then everything works naturally. So cluster coordination, this is one of the things I alluded to earlier. The two things I mentioned that make this possible and very powerful are the notion of the workflow ID uniqueness that I mentioned. So when you create a workflow, you can either ask Temporal to assign a random workflow ID, or you can assign one yourself. There's limitations on, not limitations, the platform guarantees that there'll only be one workflow ID instance alive at any point in time, right? So if you try to back-to-back create two workflows with the same ID, the second one will fail, it'll get an exception. So based on that, plus the notion of signal with start, which is the ability to send a signal and simultaneously atomically start a workflow if it's not already running, give you very powerful primitives for building cluster coordination mechanisms. So, you can do things like, there's a general mutex pattern that the temporal documentation talks about, and I implemented it in Clojure as well. So there's a link up here to the sample for that to show how that works. Actually, I've since refined how I do mutexes within our own production code, so I'm going to update the GitHub one shortly. But the one that's there is not bad. There's just a few extra features in the one I have internally. But anyway, so mutex pattern, and the basic idea with the mutex pattern is essentially, you have workflows that can be created with arbitrary IDs that may lock one or more resources based on the resource ID with the mutex work. So there's actually a separate workflow for the mutex. So when you're doing this pattern, for a given operation, you're generally firing up at least two workflows, one to do the operation and the other to lock, to basically coordinate the operation. So as we can see here, I've now made my silly financial accounting a little bit safer by actually acknowledging that, you probably shouldn't do the read modify write outside of a critical section, leveraging that mutex concept. So in this case, if you were to take a look at this code, you kind of get a sense of what I'm doing here. But the account ID in this case, I've chosen to use as my resource ID, so I'm locking at the granularity of on a per account basis, and then performing my read modify write. So now I'm able to do it safely because I know something else shouldn't have come through and done an account write. The account read is now part of my event log. Nothing else should have been able to mutate the database while I'm in that critical section. That's one way to do it. The other way, there's two variations of the second theme, which are basically, instead of having a separate workflow for like the mutex governing your access, you actually use the primary workflow as the coordination point. And we actually do that in one of our data path services. So, actually those vaults I mentioned. So we're sending, a graph update to a vault. We actually organize the mutation commands based on the vault identifier. So the workflow ID ends up having the vault identifier incorporated into it. And so basically, we're queuing commands to the vault based on the resource ID. So there's a few different ways to do it. Both of them are based on those same fundamental principles of guaranteed uniqueness and signal at start. Very, very powerful though, because you don't need to have something like etcd or zookeeper or other cluster coordination primitives available. We can actually just do it right in Temporal, which is kind of awesome. One other thing I should mention too is related to fatal error handling. First, before I get into this, what I should say is like most of the SDKs, well, when I say most, I know Go and Java. I haven't looked at most of the other ones, but at least with the Go and the Java SDKs, there's a general notion based into the Temporal SDK of kind of registering whitelisted exceptions, right? So, and the reason why we're even getting this conversation is something else I should have mentioned, which it has to do with Temporal's retry policies, right? So there's a notion of a retry policy. So I can say, workflow X calls activity Y, and it has this retry policy, and you can see it with a sense of like what a retry policy might look like. Like you're specifying things like how many times to retry, this exponential backup. There's all different parameters for it. But for certain things like non-fatal errors, like say if I, to go to my original example of I'm doing a database update in a Kafka message send, let's just say my database went down for 5 seconds when I tried to do the write. So, the activity on sending the database write out might fail. And that would be presumably non-fatal because the database hopefully comes back at some point. So you can have Temporal retry that for you, right? So the activity goes, you invoke the activity starts running, it can't find the database, it throws an exception. Temporal will actually automatically, according to your retry policy, start trying that activity again and again, or whatever your policy is. Like you might say it's try it 3 times or try it infinitely with exponential backoff, whatever. But there are cases where you don't want it to do that, right? So, and I actually found this, maybe this will be obvious to everyone else, but I found it counterintuitive when I first realized it. But you actually want special handling for your fatal errors, because you want to basically say, these are the ones I don't want you to retry on. I always think of like, fatal error seems like you should just die, but no, it's in this case, you actually want to handle the fatal errors because you don't want it triggering Temporal's automatic retry policies, right? So in this example here, I'm saying, okay, well, if the account's not found or you have insufficient funds, no amount of retry is going to fix that. It's just fatal, right? So I'm explicitly handling them. And to my earlier point about like the Golang and Java SDK, those SDKs have the notion of kind of a whitelisted set of exceptions that should not be retried. Now, obviously, given that we're based on the Java SDK, I could have leveraged that. I didn't, because I couldn't really figure out a good way to express, the Java exception classes that made sense in Clojure. It was just an impedance mismatch between, expressing a list of Java exception classes in the way Clojure exception handling generally works, which I tend to use Slingshot. I don't know what folks usually use, but I use Slingshot, so I'm throwing native Clojure native structures like maps and things like that. So at some point in the future, if I can get clever enough, I might find a way to maybe integrate like Slingshot type expressions in a similar way that the Go and Java SDKs do whitelisting. But today it doesn't exist. So I kind of do it explicitly similar to how I've done it here, which is, I kind of catch and recast errors as something that's nippy and codable, right? So, I tend to use a structure like this, where there's a vector, and the first thing is either okay or error, and then it follows with extra information. Your mileage may vary. There's a bunch of ways to do it, but essentially the gist of it is, I'm catching fatal errors and throwing in and casting them into nippy and codable things that I then interpret on the other side. But generally speaking, you want to do something, because if it is a fatal error, you don't want the thing going through exponential backoff on insufficient funds. It's just never going to pass. That just doesn't make sense. So you're putting those things in something like this, and then you're in good shape. Generally speaking, on this topic, you probably want to manage your retry options. We don't really go into it too much here, but one of the things we use Temporal for is like Saga pattern orchestration. So we're like, the workflow starts by doing some set of operations, and if anything fails, we're undoing it with compensating transactions. And generally speaking, like you're going to want to have a different retry policy on your on your do versus your undo, because the like basically I don't know if I say conservative. I'd say it's more conservative on the do side, where I'm saying, try to do this, a maximum of 3 times. But then if you end up in the undo state, I want to be super, I want to allow it to try a lot to undo it, because I'm in an inconsistent state at that point. Right? If I fired off, 3 different requests to 3 different microservices, 2 of them got through and 1 didn't. I'm now in the state where, I'm in an inconsistent state. I want to run my undo logic as long as it takes. So it might be the kind of thing where, you're screwed up and your undo is not working, but in that state, you kind of want, the system to pause, and then you can go in and correct the software and then have it make forward progress rather than just leave you in an inconsistent state. So managing the retry options is important. I find you want to kind of tone them down for, your kind of happy path stuff, and you take the defaults are, very conservative in terms of, retrying a lot. So those work well for your kind of undo and compensating logic, but generally speaking, you want to be thinking about that a little bit. So I tend to use things like this, like maximum attempts 3 on my primary happy path. There's a few things on the roadmap that the SDK doesn't cover today. So there's this concept of versioning in Temporal in general, and in the SDKs, the official SDKs, including the Java one. What that means is that you can actually have different versions of the workflow declared at a time. So remember earlier I mentioned, you really need to think of it in terms of a contract, right? So if you release a workflow into the wild, and like my first example of it comes up and it does activity B and then activity C and then exits, you shouldn't introduce a change to your code that then suddenly calls activity D, or let's say activity D goes between B and C, whatever, because now you've broken the determinism of the workflow. So if you do that and you get lucky and there are no pending workflows that need to be replayed, you'll never notice. But if anything happened to have been in the middle when you injected that change in your software, Temporal is actually going to throw an exception for breaking determinism. So the way you handle that is by versioning the workflows, and so you can actually release V1 of your workflow, which had your original B then C, and then V2 of your workflow that has your B and then D and then C or whatever. So I do plan on supporting that probably in the very near term. My thought is I'm going to do it with multi-methods, so it'll be kind of like the def workflow macro you have now. Maybe it'd be def versioned workflow or something like that. And the idea with that, you can supply def method workflow X V1 and V2 or whatever. So you'd have like a multi-method dispatch for the versioning. I haven't built that yet, so it doesn't exist. So if you're working with it right now, you'll have to be careful about changing your contracts because the version support's not there, but that's coming. There's a notion of queries. So queries are kind of like the read side of signals. So something can send you a query, you can receive it in the workflow, gather up some response and send the data back. I think these are important for a lot of folks that use Temporal in general, especially if you're relying on Temporal as your primary persistence layer. At Manetu, we have a separate data, we're doing that CQRS kind of pattern where there's a database there. So we're using Temporal to govern access to our database, but queries we satisfy through the database. So the query interface via Temporal hasn't been a priority, so it's not built, but that is something that a lot of users of Temporal do, and so I want to support it through the Clojure SDK at some point as well. That's a little less important to me, so I don't know if I'll get to it as quickly as versions, but that's there. And then child workflows is actually probably pretty easy to implement. I just haven't bothered yet, but I basically just need to expose the child workflow methods to the SDK. It's not much work, so I'll probably put that in soon as well. That aside, you actually can, so you can always invoke anything you want through interop, right? So the notion of calling the Java child workflow method it is accessible to you. You can do it. It's not been clojurified by my SDK. So I just plan on putting a Clojure interface in for that. But other than that, I think generally speaking, we have pretty broad coverage of most of the SDK. There's a few things that in the SDK that I didn't talk about here. I ran out of time, like data converters, for instance. So data converters, if you're curious, are something you can read about in the temporal documentation. But the gist of it is that you can put, these basically extreme processors in your clients so that data in and out of temporal, so as we've talked about, values going in or out of workflows and activities gets put into the activity log. So data converters are a way for you to apply some transform to that data. So it's useful for things like encryption, like that's what we use it for, because we don't want, we're handling sensitive data. We don't want, clear text data going into Temporal's Cassandra database. So we'll run a encryption data converter, et cetera. So there is a notion of a data converter in the SDK, but I didn't cover it here. I can't think of anything else. We pretty much covered all the major pieces. Oh, unit testing. Yeah, so there's a unit test facility in the SDK as well. Again, credit goes to the Temporal community. I'm largely leveraging the Java SDK's unit testing facilities and wrapping it in Clojure kind of idiomatic mechanisms, but it is here and it is very robust, and we use that in production as well. So this is kind of that same hi Bob hello world example, just written in unit test style. So you can see, I've just got a def test calling some things. Few minor details would be there's this temporal testing env namespace that has some unit test friendly constructs in it. So you can see here, like one of the things I'm doing is I'm calling eCreate to create an environment. And then from that environment, I'm creating a client instance, right? So, as you can imagine, in a real app, you've got this client that's expecting to connect to a temporal cluster. So in the unit test thing, we want to create, a mocked temporal backend, et cetera. So, the eCreate essentially creates that mocked backend, and then from that, I'm calling get client that hangs off that environment, so that I have a client that's already connected to that mocked thing, as opposed to trying to connect over a DNS name. So there's a few minor differences like that, like getting the client from the environment, et cetera. But otherwise, it works. Oh, and then the other thing I guess I'd say is eStart simultaneously starts the mock backend and starts your worker instance, right? So there's small nuances that are different, but pretty much after you get past these first three lines, it works exactly the same as the normal SDK flow. So like, again, create workflow and then start and then get the result. It kind of works the same. So this works great. We use that heavily in our CI pipelines to test all this and get great code coverage just at the unit test level, which is always desirable. So that's available and works today. So for the last part of the talk, I'm going to do a demo. I wrote this app that's up on my GitHub page, Haskins reminder bot. So what this thing is a really dumb chat bot that I wrote for Slack because I needed an example and I was kind of curious how the Slack API works. So I cranked it out over the weekend. It's pretty dumb, but it does work. So it's up there and you can check it out. There's not a lot of code in the bot, but it's more than what this capture on the right implies, because there's some setup for the Slack API and blah, blah, blah. Most of it's not important for this conversation, which is surrounding the temporal stuff. So this is the temporal specific parts to it, which you can see, I'm always a huge fan of Clojure's concision. So I'm proud of this being 43 lines. But, in a nutshell, what this thing is doing is, it adds a new command to Slack called remind me, and it uses an NLP entity extraction library called Hawking to find some time reference and basically does entity extraction into two pieces: one, a timestamp, and two, the non-timestamp part. So I'm using that library to build this chatbot where you can just say silly things like, remind me to take out the trash in 10 minutes, and it will basically DM you back in 10 minutes when that's expired, giving you the message that you gave me. So take out the trash. So again, pretty stupid, but it does do a decent job of giving us a little app to play with temporal. So to that point, here on line 35, this is the function that Slack ultimately invokes when someone types the command into the Slack window. So this kicks us off running. You can see here on line 39, the second step, that's where I'm calling that entity extraction library to parse out the time and the phrase information. So not really relevant to temporal, but that's what's happening there. Line 40 is where the temporal relevant stuff starts to happen. So this launches, calls this launch workflow function, which is up here on 30, which you can see is now the now familiar two-step process of creating a workflow and starting it. Now you'll note that I am launching it and not calling get result because I don't want to block this waiting for the result. It could be running for, like in my last example here, it could be running until tomorrow morning. So I'm asynchronously launching the workflow. And then if that all works, I'm telling Slack, okay, print the message that they'll be reminded at the time they ask for it. So, just looking real quick, up here, I have a workflow and an activity. So my workflow on line 25, that's a 2-line workflow, super simple, uses the sleep primitive. So there's, as I mentioned, there's different blocking and predicate. There's a predicate based await, there's a sleep for duration. So there's different ways to wait on time, and you can wait on a signal with a duration, timeout, etc. So in this case, I'm just using the sleep primitive because it's part of the SDK, it is safe to do. And I'm specifying, I have this helper function duration from now, which is just using the Java time library to compute the time difference between now and the deadline that was extracted by the NLP software. One key point about that I'll point out here on the note 5 is I'm using the side effect API, right? So the notion of getting the current timestamp, I'm using the side effect API to get that in a safe manner, and computing a duration for the sleep. Now, as you probably can guess from all the conversation we've had, is the SNow side effect will compute the current, basically the Java time instant in that moment it was asked for. But that's only going to happen on the first time this workflow runs, because if we're running it from a replay, it's going to get replayed from the log, which is actually what you want. So this thing is all relative to the first time it was run. We get a timestamp that computes a duration from now in seconds. So let's just say I asked for 10 seconds from now. Roughly speaking, this thing comes up. It says the time is now, the deadline's 10 seconds from now, the duration is 10 seconds, and it calls sleep with a duration of 10. Now, if this code were to crash and be restarted, 5 seconds from now, the replay is still going to come up and say replay the sleep with duration 10. But it's actually, Temporal knows that you're not making a new call to sleep with the value 10. You're replaying the existing call to 10 sleep with the value of 10 that happened in some time in the past. So in the event log, it actually knows there was a sleep request that expires at a certain time. So that expiration actually is baked into the workflow. So it actually, the sleep is programmed to wake up at the right time, no matter when we rerun this program, which is, it's a little bit different way of thinking about it, but it actually ends up making things a lot simpler. That concept makes things a lot simpler in general. So anyway, this workflow is super simple. It just sleeps for some number of seconds and then calls the activity send reminder and invokes the send reminder activity, which of course just calls Slack to post a DM. So what I'm going to do now is just show you guys this in action. Let's see here if I can bring this up. All right, so a few things. So one of the things I'm going to do is I'm going to launch an instance of Temporal Lite. So Temporal Lite is a community project that takes the whole temporal backend and runs it all, basically all the microservices of Temporal. It combines it into one binary, so you can just launch it, and it works with ephemeral, or I can't remember the other database they support, but it's not meant for production. It's great for testing. The performance of it is actually pretty bad, so I do not make any kind of assessment of what Temporal's capabilities based on Temporal Lite. My experience with the performance side is, if you're doing a onesie twosie, it doesn't matter, but if you try to pound on it, you're going to be disappointed. Whereas temporal itself is actually super high performance. So, you're gonna do performance testing, use the real deal. All right, so that's running now. Like I mentioned, it's basically like temporal in a can. Everything's up and running. I've got an ephemeral service. Over here, I refresh this. I'm now bringing up that UI that I mentioned. So because I just launched an ephemeral temporal light, there's no workflows. You can see that confirmed here. So we're in the idle system. So this window here is my REPL for that reminder bot. Actually, so before I start that, let me, I couldn't really clear my old history, so you can see some of my earlier tests. I apologize. But so if I do remind me, this is not going to work because I'm not running the code right now. But this is kind of showing you it's not smoke and mirrors. So if I say, in 10 seconds, I should get an error. It says, oops, sorry, remind me in 10 seconds. So it said dispatch failed, and that's because I'm not running the service, right? So what I'm going to do now is fire up my REPL environment, and I've already set up, I've installed the reminder bot into my Manetu Slack environment here, and I've set up the API keys for that bot into my REPL. So if you run it yourself, you'll have to, set up the Slack API keys yourself. I don't share those for good reason, but you can do that if you wanted to. Anyway, so I've got my bot running now, and you can see, so I use Integrant. I don't know if you guys use that or not. It's kind of like Component or a few other things, but managing my startup here, I just want to point out a few different pieces. So you can see, here's the reminder bot event loop. So this is the thing that's waiting for Slack events. And then this is my temporal worker. So that starts up the temporal worker. So my code, that we just studied that has the schedule reminder and send reminder workflow and activities are now registered and running. In fact, you actually can see I turned on the temporal SDK logs too. So this init you can see is registering the send reminder activity. So there's some fully qualified name details about where the function is in the namespace, etc. Then you should be able to see the workflow too. So there's the auto registration thing happening in the background. Normally you don't need to care, but just I pointed out. So my thing is now running. So it's logged into Slack. It's waiting for events. It's fired up the temporal worker. It's waiting for workflows to be invoked. So I'll go ahead and do that again. So I'll say test in 5 seconds. Right. So you can see now, I got back my message. Okay, I'll remind you to test, and you get the extracted timestamp that it inferred from the word 5 seconds. And you can see over here my bot, did in fact reply to me. And my entity extraction is not perfect. It sometimes gets confused about in and at and use them in the message. I apologize, but you get the gist. So I just told it to, send me a message test in 5 seconds or whatever. And that ended up creating the temporal workflow, sleeping for 5 seconds, and then sending a message. So if we were to refresh over here, we can in fact see that workflow ran and completed. You get the history of it, right? So there's the schedule reminder workflow being kicked off. There's the side effect of me computing the current time. Then there's the timer, the sleep, basically under the covers, does a timer instruction to temporal, and then it should be 5 seconds later the time of fire, right? So it came up and invoked the basically woke up the workflow that invoked the activity, which we should see here, the task scheduled for a send reminder, and that ran. So all of these things are the event history of that particular run. One of the things that's some of my users have complained about, and I don't disagree with them, I just haven't had a chance to fix, is that because I'm doing NIPI encoding, you can't really see, can't introspect the values like you might in most SDKs, which is a little bit annoying. There are ways to fix it. They have this thing called a remote codec server. I probably will build one at some point so that it can decode these values, but it's not implemented today. So long story short, temporal is dutifully recording your state into its event log, but you can't easily introspect it because it's NIPI encoded. Anyway, so that's the thing. What I really want to show, because I think this is cool, is I'm going to do a slightly more interesting one. So I'll say remind me. So the time is it's 8:01. So say remind me at let's say wrap it up at 8:03 p.m. And so it just ran. It's now scheduled to remind me. I'm going to kill this though, right? So my REPL's here running the thing. I just killed it. So now it's not running anymore. If you go over here to Temporal, you can see the workflow is still running because I scheduled the timer for 2 minutes out. So I'm going to just restart the REPL. You don't have to do anything else, just start it. And that thing should still fire, right? Because that Temporal's worker reconnected to the task queue. When that event goes to expire, it's going to see it's available and kick it off. So, totally resilient. I just killed, the REPL, restarted it, and the logic is none the wiser. Still the workflow is still just sleep and then send. Didn't have to change anything. Didn't have to do anything different. I just started the program again, and it will pick up right from where it left off. So, really kind of awesome. If you're in the space of needing resilient, fault tolerant processes, I found it pretty Temporal's story is pretty compelling. Like, it just super simplified. Oh, there it goes. It just fired. So you can see eventually the thing ran, and you can see my reminder came in. And if we look at the details here, you can see this is where I resumed the rep. I restarted the REPL, right? So this timestamp was 0212. So you can see this block of activity is the new stuff, right? So the interesting thing here is that from the flow perspective, we actually see the workflow being started again, right? So from our program's perspective, the schedule reminder workflow was started again, and then ran to completion. So that's the replay logic coming in, basically rehydrating the state, having the program run through. Now, it doesn't need to recompute the time because that's already in the side effects already in the log. It doesn't need to re-register the timer started or whatever the event's called. That's already in the log. So it basically caught the process up to where it had been, which was waiting on the sleep function, and then it continued on, which in this case happened immediately because the timer was already expired at the time that was scheduled. So that's all I have to show. I'm going to go back. I think I just had my thank you. Yeah. So that's all I had prepared. I've been talking a long time, and I apologize. Mark, how do you want to do it? It's just 2 questions, or?
Oh, yeah, that's what I was thinking. So, by the way, thank you for tremendous introduction, both concise yet pretty complete of Temporal and your SDK for Clojure for using it. Really highlighted some of its excellent properties, and it seems to have terrific potential for improving resiliency of distributed workflows. Really impressive system. So yeah, hopefully some of our viewers will have been thinking of questions as we go. I know I did. In fact, about half of the questions that I came up with, you answered in the course of your presentation. So that's a little frustrating, but also speaks well of the presentation. So yes, let's open it up to questions. Who would like to go first? We often have a little shyness at first, so people are probably thinking a little bit.
Yeah, the mute is automatic, so you might have to unmute yourself if you wanted to say something.
Very much so. We'll give it.
I have a question that's probably very naive, because the level of software that I interact with and teaching is quite different. So this is all although overwhelming. But the question is, so you mentioned that it doesn't handle things like non-determinism really well. And you mentioned that with some of the ID stuff, like if you happen to generate two of the same ones, then it sort of breaks and throws an exception. But
Yes, I would say it's slightly different in that you have to
Right.
be cognizant of non-determinism. It's not that it can't handle it, right? There are ways to deal with it. You just have to be aware of it.
Right. But I guess my question is, if you do something silly, it's not gonna notice, right? So you're just gonna.
I think it's pretty good. So I mean, if you do something that violates the determinism of your workflow, you'll get called out on the very first thing you try to do, right? So like my example of, you had invoked B and then C, and then you change it so now it's B, D, C or something like that. Like it will throw an exception as soon as you try to invoke D. Like it will know. So let me clarify that. It can only detect up to what's already been played in the past, right? So if your workflow is 75% through, and then you do something non-deterministic in that first 75, it's going to call you on it immediately. Now, if you did something, where you introduce new non-determinism later after the point that no log has been generated, it can't tell, right? So you're going to get away with that one. But generally speaking, I mean, you just want to be aware of like, all right, you have to write deterministic code, and you want to do it a certain way, and not not try to get away with it. Not that suggestion I know that's not what you were suggesting, but generally speaking, like if you do something that violates the non-determinism, or if you do something like sleep with a normal synchronization primitive or anything like that, you're going to get an exception right away. Like the runtime will detect that. So it's more, I think it's more of being cognizant of what the limitations are or the structure needs to be and doing it that way than it is that it's not detected.
Mm-hmm. So something like when you're trying to do some sort of key generation thing and it's interactive, it's either going to do it correctly or it's going to sort of throw something.
And most basically the answer is most things you want to do in an activity, right? So if you had like user interaction where you're trying to do key generation or whatever, you'd want to do it in an activity. So when you're in an activity, it's like all options are on the table. You just write normal code, so you can send gRPCs and write to databases and interact with the user or whatever you want. But there are, depending on how you want to structure it, you may want to break like just like I did with my the debit account, moving it to have two different activities. You may want to structure things like that so that you can take advantage of the write ahead log, right? Because that's really what it's about, is like Temporal is basically, I've been trying to think of a good way to describe it. Like I used to work in the telecom industry, we're building fault tolerant networks and things like that. And so we would have write ahead logging or intent journals all over the place, but you're doing it very explicitly. Like I have this, I'm going to write this log entry and then I'm going to do it. And then during recovery, I'm explicitly reading my log and playing it back. And Temporal has kind of taken that. It's almost like, I almost want to call it like an active intent log. Like it's like I'm writing an intent log as Clojure code. It's like, I don't know if that really captures it, but it's like my code is the log. And so you want to take advantage of that as much as you can, or at least for places where you need it. So, you may want to restructure things just for the purposes of taking advantage of the journaling, but you don't have to. I mean, you could do it, I do this all the time where I've had, I'm using some Java interrupt for something or whatever, and it has no idea what temporal is or, I think it's constraints. So when that happens, I just put it in an activity and it all just works the way it always did. But, I'm strategically moving things, from an activity into a workflow when I really need that structure of that, the write ahead journal that I get kind of for free.
Very cool. Thank you.
Excellent.
Hi, Greg.
Anyone else? Go ahead.
Yeah. Hi, Greg. I don't know if I missed this. In your demo there, where you your last demo where you took down the REPL and brought it up after you put the remind me in for 803 to say wrap up. Did you you may have covered this and I just missed it. What would have happened if you would have restarted the REPL after 803? The temporal light server, would it have
I think it
failed
would have fired
and then retried again right away or something?
I think it would have just fired it late. Like I think it would have just been, it's already expired. So if you want to do remediation for late events, you would actually probably put extra logic in to say, don't call the invoke if it's after 803, something like that. But it, my logic was super simple. So I think what would happen, I have to confirm it, is that your sleep was set to basically say sleep for 10 seconds or 2 minutes or whatever, and that essentially translates into a timestamp that the sleep will wake up. So if I started the REPL at 8:05, it would have already been satisfied and just fired fired immediately. You would have to do extra remediation if you want to have it not fire.
I see. Thanks.
Right.
Anyone else? Well, while you're thinking, I had sort of a tangential question.
Sure.
So you may have heard of a tool called Jepsen, created by Kyle Kingsbury. It's essentially stress testing of distributed systems,
Okay.
and in virtually every case that the tool's been run against such a system, claiming having to have perfect distributed consistency, he finds bugs in that.
Right.
What level is Temporal at in terms of its quality? Have you found actual bugs in its?
So the quality is, the short answer is I don't know how it would perform under that test. It may have been tested under it or not. I don't know. My experience with the quality. So what I meant to add, and I was thinking of it earlier today, and I was like, it's too late to change my slides. But I didn't give a history of Temporal itself. So Temporal itself, my understanding is it was started at Uber maybe 12, 15 years ago. And it was an internal project that they eventually open sourced. And then I think the folks that architected it split off and created Temporal as a company to offer it. So they, it's an open source project, but they also have a cloud offering and things like that. So it's a reasonably mature project. It's not, it's not 6 months old or anything. It's been around a while. My experience with it has been extremely high quality. I've been dealing, so at Manetu, we build most of our stuff with Clojure, and we have a little bit of Golang. And we did find one bug in the Golang SDK that's still outstanding. But other than that, the Java SDK on which the Clojure SDK is based on has been rock solid. Temporal backend has been rock solid, and aside from that one bug in the Golang, that's been solid. So I think it's a pretty solid product. Like I said, I don't know what formal testing may or may not have been done. I'd be curious. I'm gonna go look that up now. I'm just curious what if that's been done. But it's in general. It's my SDK is pretty new, but Temporal is not. Right? It's been around quite a while. It's pretty solid.
Oh, great, good to know. Thank you. I actually did a quick search, and I didn't find any Jepsen result for Temporal, but that would be really interesting to see how it fared. Almost everything seems to crumble under its load.
Right.
So, what else we have out there? Comments, questions?
I had one question. Early on, you talked about the retries.
Yep.
And certain retries you want to retry a lot more than others, and certain retries you just kind of log an error and move on.
Right.
For the retries that are so in our systems, we're building stuff, talking to Kafka, REST APIs, cloud data sets, and stuff like that. And those can periodically have outages that are maybe a minute or maybe 6 hours, stuff like that. So how do you determine how many retries for stuff that is actually critical to the thing succeeding?
That's a great
what
question.
What do you do if you need to really end it and move on? And
that's a great question. So I alluded to the fact that we use kind of like a saga pattern in a lot of our code, right? So basically orchestrating some kind of multi-pronged transaction that may need to be undone with compensating transactions, right? So I can give you a concrete example. I mentioned we have this thing called a vault, and we have a vault service that's job is to be the arbiter for, you know, the life cycle of vaults, creating, deleting, listing, etc. So when you're creating a vault, we actually have to talk to, we have a key management system, we have an access management system, we have a database in the vault service representing the vault, etc. And and then actually there's that expiration workflow I talked about. So for, you know, creating a vault might involve kind of 4 legs, right? Key management, access management, local database, possibly expiration workflow. And so in the workflow for creating a vault, my what I call the do logic, you know, the roll forward logic, has basically a parallel, you know, p-all for firing those 4 things at once. You know, so I'm key access management database thing all go out at once. And now normally in the happy path, all 4 succeed. We aggregate the result and continue on, and we're done. But if something were to happen, we have to potentially undo a partially committed state. Like maybe the key management system created the key, but the access management system failed for whatever reason, right? So when that happens, we go into our undo logic to, you know, basically do compensating transactions and say, okay, the access management failed. I'm going to undo the key that was created. I'm going to undo the database row that was created. I'm going to cancel the expiration workflow. So we have that basic pattern kind of repeated all over the place. So in that paradigm, I'm kind of using 2 different retry strategies in the 2 groups, right? So in the do group, I do things like I'll set the schedule to start timeout to be something finite, like say 30 seconds. Like, so I'm going to fire off those 4 requests, but if they don't actually start within 30 seconds, just give up. Like the system's so overloaded that you can't make forward progress, so just give up on the whole thing. I'm going to set the retry to something finite, like try up to 3 times to create a key, try up to 3 times to access, you know, set the access management, etc. And so it's very easy to give up. I guess the do logic is kind of like it will give up fairly easily. The undo logic will basically never give up, right? So like if we're in a state where, you know, all right, I've created the key, I failed at creating the access control policy, I created the database record, the undo logic will basically retry the undo compensating transactions forever. I mean, it would basically go into like a, you know, very long, you know, forever means like, you know, whatever the, you know, Kafka expiration window, you know, 2 weeks retention kind of time frame. So I'll say that, you know, retry with an exponential back off for 2 weeks. And that's the idea being that, you know, if it's some kind of thing that we can't repair through automated compensation, we want to go in and manually clean up the partially committed transaction, right? So I think that kind of gets to what your point was, really, like in that undo, you know, I'm changing my policy to be, you know, I'm not being aggressive on the do. I'm saying, you know, try up to 3 times and then give up. And on the undo, I'm being very aggressive and saying, don't give up until you've undone it. And if it can't actually make forward progress, you know, you want to be alerted to that and then come in and, you know, manually remediate. So that's the kind of strategy we take overall. That kind of gives you that, you know, I mean, most of the time what ends up happening is nothing fails and it works, right? And then in a very small percentage of the time, something fails and the compensating logic works and undoes it, and you continue on. And then, you know, in the really bad situations, you know, the compensating fails, and then that's when you're going in, you know, 6 hours later and fixing the, you know, fixing up the database records that got messed up or whatever, and moving on. But you know, that gives you kind of all 3 levels of option when that happens.
So a follow up on that. Oh, sorry.
I was just saying, did that answer your question?
Yeah, I had one follow up. I don't know if that's
Sure.
similar to
course.
Mark, but you talked about using Nippy to serialize some event data,
Yep.
and then using that to replay. Because how are you persisting that, and like what is your strategy for going back and finding errors that occurred and trying to redo them?
The Nippy data itself?
Or just like how are you storing that and replaying it?
So Temporal does that for you, right? So when you call, let me bring up my code here again. So when you call, all right, so you get this, I'm gonna use the non-unit test version of this. So we got this like Hello World app here, right? And so line 21, I'm calling start workflow with the parameter name Bob. So this map with the contents name Bob under the covers would be serialized with Nippy, and you would see that in the event log as that encoded base 64 data that I mentioned, right? So when I call start, that gets serialized and basically ultimately stored by Temporal in its Cassandra database as part of the event history, right? So now you see this, workflow execution started. Again, this is just a screenshot, so I can't expand this, but if I expanded this, in here would be the encoded version of this data, this name Bob. So that gets persisted in Temporal's event log in Cassandra, and ultimately, sent across the wire on the task queue to the worker, which gets rehydrated and expanded through Nippy unfreeze or whatever Nippy calls it into the arguments here, right? So the gist of it is that Temporal's persisting all that for me as base 64 encoded bytes. I don't have to deal with it. I'm just thinking, when you're using the SDK, you're just thinking kind of Videomatic maps and keywords and things like that, but Nippy is persisting it through Temporal's event log. Now, obviously, I have other types of persistence that are outside of Temporal, and we have strategies like protobufs and stuff like that for storing it there, but that's outside what we talked about here.
So is the happy use case the same as the error use case, where it gets stored in the event log and you read it there and then process it?
Yeah, like to go back to my bot example here, right? So as we saw from when I killed the REPL and then started it again, this is the logic that was being run, but I'm not differentiating between first try or nth try, right? I just write my logic. And the way Temporal works is essentially, they'll invoke this function each time, and they'll replay things that have already succeeded. So like on the first, when we ran this, the first pass through would have called the side effect for now, getting the current timestamp, and then called the sleep routine, which essentially registered the timer with the time that it's supposed to wake up. That became part of the event log. So when I killed the REPL and killed this whole program and then started it again, this thing hadn't run from Clojure's perspective, right? But then Temporal reruns the thing and essentially catches the process up to where it had been by essentially returning the same values that would have been returned from the SNOW in the sleep originally, right? So I'm not differentiating between the failure case and the success case. I'm just writing this logic. This is the most complicated program, so it's not as clear. But like if you're looking at like one of these other ones here, where maybe I invoked 3 activities in parallel, and then in here pretend I was like calling some other invoke. To maybe these things compute something, and then this one sends a Kafka message, right? And let's say we died right here, so A, B, and C had completed, but the Kafka message hadn't been sent. So from the perspective of this logic, I'm not differentiating between successfully running the first time or retrying, but it magically catches me up, because when Temporal runs this in the retry scenario, the values that were returned from invoking A, B, and C are just populated. The invoke just has the result already. It's part of the event log. So it catches me up without actually calling A, B, and C again. And then I would call Kafka and continue on, right? So you really don't, like I said, if you wanted to, you can ask for the metadata from Temporal. It will tell you like, this is the nth retry, but generally speaking, you don't have to care. You're just kind of coding this way. And it flows through correctly, whether it's the first time or nth time.
Great. Thanks, that was very helpful.
Yep.
So my follow-up, I guess, was quite an edge case, but if you had a disastrous failure and you had to restore the database from a snapshot, Can you actually truncate the Cassandra log and go back in time and say, try Tuesday all over again or something?
Yeah, so I haven't tried any kind of advanced kind of recovery scenarios like that, but my understanding is that there's actually all kinds of really neat things you can do of that nature. Like it would be a question for the temporal community, but like you can rerun, if I understand correctly, like you can actually rerun an old workflow, all that kind of stuff from the event log. There are some limits, so that I think the default is it retains for 30 days or something like that. So if you don't change the defaults, you're not going to have more than 30 days worth of history recorded. But if you're within the window of retention, there's all kinds of things you can do in restarting a workflow, restarting it from a certain position, that kind of thing. I haven't played with any of that though.
Yeah, that'd be super useful for regression testing too, to be able to go back and
Absolutely.
replay.
Yep.
So, all right. Anyone else? Going once? All right, why don't we stop the recording here